Hello, everybody. Welcome and thank you for joining us. I'm Roberto Martinez with the Wolfram U team. We're ready to start the 2026 Wolfram System Modeler User Conference. Before we begin, let me share a free System Modeler trial so you can test some of the features that you see in these presentations. Let me share that with you right now. And I would also like to remind you that you can download today's presentations by clicking the link in the right part of your screen, where you'll also find the Q&A. Use the section to post questions and comments during today's conference. Please note that this session is being recorded and will be sent to your email later today. And for those of you watching on YouTube, feel free to post your questions in the chat and we'll get them to the presenters. Thanks for answering that poll. Let me share the results with you so we can see the audience. This is the answers of the poll. And thank you very much for letting us know which best describes you. So without further delay, I'm going to pass things over to our today's host, Ankit Naik.
Hello everyone, and welcome to the Wolfram System Modeler User Conference. My name is Ankit Anurag Naik, and I'm an applications engineer working with the Wolfram System Modeler team. Today's sessions will focus on how System Modeler is being used in practice across aerospace, electric vehicles, water infrastructure, and industrial digital twins to support model-based design, simulation, and optimization. We will begin with a brief overview about System Modeler, followed by 5 user presentations. Each talk will be followed by a short Q&A. So let's start with a high-level introduction to System Modeler from Jon Bruegel. In this talk, you will see how Modelica, Wolfram Language, and FMI integrate into a unified workflow for modeling, simulation, optimization, and digital twin development. So let's get started. Over to you, Jan.
So, System Modeler is a software about curiosity. You start by doing what is necessary, then you move on to do what's possible. And before you know it, you are doing what you thought was impossible. In 1985, the cosmonaut Vladimir Janibekov was tasked with a rescuing mission of the Salyut 7 space station. While unpacking supplies sent from Earth, he loosened a wing nut that was locked onto the bolt. As the wing nut came off, he noticed that it kept its orientation for a short time and then suddenly flipped 180 degrees. This phenomenon, often referred to as the Janibekov effect or the tennis racket theorem, has been known for more than 150 years. Still, for most of us, it defies common sense. What could cause this effect? And can we reproduce this behavior? Hello, my name is Jon Bruegel. I lead the development of System Modeler. Already as a child, I enjoyed building models. At first, I also built houses and animals of different kinds. Later, I moved on to cars, aircrafts, motorcycles. Eventually, I started building mathematical models instead of using Duplo and Lego bricks. A few years ago, when I saw Veritasium's brilliant video on the Janibekov effect, the bizarre behavior of rotating bodies, I became curious and wanted to see if I could reproduce this phenomena in System Modeler. I will use this example to introduce the basic concepts of the software. I actually did a recording with all the mistakes I did and so on, so you will see that soon. My first thought was, what is the quickest way to see, to reproduce this? The multi-body library seemed to be a good starting point. So I opened System Modeler, went to this multi-body library, and started modeling. So let's see what happened. And I'll comment meanwhile. So I added this world component, which is basically a place where you set things like gravitation and global properties for your system. Then I added a couple of body cylinders, 3D masses, that I thought together would be nice in order to get a shape similar to T-handle. And to connect these with 90 degrees, I used this component called fixed rotation. All these from the multi-body library. Then I started to connect the system. And that's basically it. The only thing I needed to do now was to set the proper parameters for things, like starting by setting gravity to 0, because I wanted to go to space. Then for the handle, I decided, let's do it big. Doesn't really matter how big it is. I did it 1 meter. So that's basically a yard. And then 20 centimeters in diameter. Then I went over to this component that was supposed to center the next connection. So I called it center. And I wanted to rotate 90 degrees. So I got the T for the T handle. So I rotated around the y-axis 90 degrees. And then went to the shank. In the shank, I set it to half the size of the handle. But I think I decided to set the same diameter. We'll soon see that soon. Yes, 20 centimeters for that too. And then I realized, yes, right, I forgot to set the distance into the center. So I did that, and now I was ready to initialize the system. So I had this T-shaped object. The only thing I needed is to get it to rotate to begin with. So I said, let's get it to rotate around the x-axis with 10 radius per second. And then I simulated. Once simulated, there's plenty of things I could plot. Like every single variable in the system is available. But what I choose to plot was the rotational speed of the shank. So I dug down to find it, W here, and we can see, quickly see, and we'll get back to this, that something is happening, it's flipping. But perhaps easier to see it is if I run the animation. There you go. In just under 4 minutes, actually closer to 3 minutes, I had replicated the Jani-Bekov effect. I got excited, and soon enough, I started to throw around all sorts of things: wingnuts, spacecrafts, space shuttles, even cats. But then I had to stop myself and say, okay, this is just for fun. Let me actually learn something. So I did what people typically do when they're trying to learn the Jani-Bekov effect. I did a point mass system. So let's look at that. The point mass systems, when I did it, looked like this. So what we can see here, I have 6 point masses, green in the this axis here, and the weight is represented by the size. There are really point masses, but we illustrate the size or the weight. I did that with size. So we see this is the smallest. Then we have the yellow ones here. They are the intermediate ones, and then the blue ones are the biggest. And these arrows, I will get back to them. So I started to plot different things. Now you see I prepared a bit of things here. I plotted, for instance, the rotational speed for the center around the y-axis here, and x and z. And we can see that flip happening. I could also study things like the kinetic energy, and also saw how that was changing for the different bodies over time. But the total was constant, of course. And then to what's the most interesting part of the Janibek effect, the angular momentum. Here we can see that for all three bodies, which is the three first plots, they are varying over time. However, if we look at the last plot, it's the total of them, and it shows that it's constant. This is easier to see if we look at those arrows there, because they are illustrating the angular momentum. So let's play that. Now, after a while, we'll see here that we'll reach the oscillation and something is happening, right? But so the blue ones represent the angular momentum of the blue masses and so on. But the total, as you can clearly see, stays constant. Now, and if you really carefully follow a yellow, well, you can see that you can actually notice a flip, right? But now I wanted to do changes. What happens if I reduce the intermediate mass and make it lighter? Yeah, then it doesn't flip because it's no longer intermediate axis. There's some small oscillation, numerical oscillation, but that's it. And what happens if we do these three weights very similar to each other, but still have an intermediate axis? Well, then it will flip, but later on. But if I increase the rotational velocity, it will flip sooner and more, all with angular velocity maintained. While this is a simple example, it illustrates something important. Even the simplest system can behave in most unexpected ways, especially when you use it in situations where you typically wouldn't be, like in space. It also shows how you would typically go about modeling your system, whether you want to model some simple system like this, or let's say the thermal management system of the Europa Clipper. It's almost always best to start with the simplest possible model first. But of course, once you invested all this time in developing an advanced model, you want to get as much mileage out of it as possible. You would like to use it perhaps for validation, for sensitivity analysis, to look at uncertainties, produce digital twins, and so on. This is where the combination of the Modelica language, which is used in the product, FMI, and the connection to Wolfram language comes in. These together is what makes it possible to take your model the next step. So if we go back to the basics, System Modeler uses the Modelica language, which is a built-in components to make it easy to get started. So just as you saw me drag and dropping there for the multi-body, there are plenty of different components for different domains. It makes it easy to create models that you can reuse in different scenarios. Whether you want to use a motor as a motor also, or as a generator, it's the same model. You just connect it, for instance, to use it in a wind power plant. Once you have your model, perhaps you want to do a system of systems, or you might want to do a digital twin. That's where the functional mockup interface helps you by exporting into functional mockup units. And I know we will see a bit of this during today. So these combined, Modelica and FMI, helps you develop systems like, here we have the energy system of Sweden, for instance, and we can see that some component of a power plant here. But you could also do a battery electrical vehicle with a battery, or you can do, let's say here, a digital twin of a oil drill, oil reservoir, and so on. All this using the two technologies, mainly Modelica, but then FMI once you want to get it out there to other places, or you want to get in something from some other software. So what happens? What about all the other questions I asked, or tasks I mentioned, like validation and so on? How would I do those? Well, that's where the Wolfram language steps in. While System Modeler runs standalone, it's actually possible to connect it directly to Mathematica, if you have a Mathematica license, and do a lot of pre and post processing of your models and results. So let me switch to Wolfram Notebook and show a few examples. I'll start here with system validation. What we're seeing here is a formation flight. It's from the movie Top Gun. I guess it's from the original Top Gun. I don't remember that, but I guess it is. So imagine you want to model this and understand different flight patterns. Then a model in System Modeler would look something like this. Or if I open it in System Modeler, this is how it would look like, right? So we can see we have a bunch of different aircrafts, and all are here set to have different missions. Like one here saying split S, which is a maneuver called split S. I can actually simulate this, and yeah, let me simulate it again. Yes, so to make sure that we have the right one running here. Yeah. So here we simulate this scenario for all the aircrafts, and let's look at how it actually behaves. And there we go. And we're following, well, an aircraft that is doing a roll, apparently, not the split S aircraft. But this way we can see how it's actually maneuvering around. But do we know that they're actually doing things within the given limits? Well, we're not saying anything about that here. So let's close this, go back to the notebook. And then what we will do is start by simulating here. I will do one that I call simulation cruise after Tom Cruise, and one standard. So we have a standard pilot and Tom Cruise here, and they do the maneuver in slightly different ways. What you can do is, in the Wolfram language, you can create expressions for your requirements. So for instance, let's say you have something like the load factor must be between -4 and 8 Gs for the plane performing the split S maneuver, right? This is just upper and lower bound, but perhaps this is actually more complicated region, like this one, where you see that, yeah, it's -4 and -8 once you go fast enough. But before that, you can't cross these limits. So after we have defined a region like this, the question is, can I now use this region to check whether we're fulfilling this requirement of never being outside it? So we will use a function called system model always, and that system model always will tell us whether, let me just move this big marker window there, will tell us whether we succeed or not. And in this case, we didn't add any probability and so on, so it was just one single simulation, but we could do that, and we'll see that later on. So one of these, the standard was within the limit, while Tom Cruise was outside the limits. But now, of course, you want to see this. Where did this actually happen? Now, when, let's say, you get a big report of different things that hopefully most of them actually pass, but those that don't, you want to study them further. So here, what we'll do is we extract the velocities for VG curves, so with velocity gravitation curve for each of the two aircrafts, and then we plot them together with our region. And now we can clearly see here that one of them, the green one, which is Tom Cruise, goes outside the limit. He's pushing it a bit too much. But being Tom Cruise, we know it's okay. While in the zooming in version here, we see that the other pilot just goes close to the limit before he returns. So from validation to uncertainties. Most systems, you don't know everything perfectly well, right? There could be different things. So if we have this system here where we have a bunch of pipes and valves and so on, and we want to study that under uncertainties, we can do that too. So you can design a parameter here that could be, and in this case, we're saying this parameter is within this interval. But this could be any expression. It could be a normal distribution or any distribution you want. That you say, this is where my parameters, how to define them. They're not one precise value. They could be any of these according to some distribution. And then I'll ask for a couple of outputs here for them, and let's see what happens. We get something like this that shows what's the median, and what's the actual spread of this. And we see that it's quite huge with the distribution we set here. And we're looking at the temperature in two different pipe sections, basically, in this one. So this way we can get a better understanding how the system will actually work with the uncertainties there is in the system. Sometimes, so system model is about, you do a mathematical model that with all its simplification, you at least you actually know hopefully know what you simplified and the precision you have and so on. But sometimes a neural net is better. Perhaps you only have a bunch of data and want to that you want to do a model for, and you want to integrate it with the rest. Then you can do that. And let me just skip forward here a bit, so we have a bit of time for Q&A. But we can see here within the Wolfram language, you could retrieve data, and then once you have gotten your data, you can say, okay, let's use part of the data to train, part of the data to validate. Let's design the neural net we want. In this case, using rectified linear unit layers, and then and method and so on. And with that, we can do net train. So let me run nettrain here. So now we are training this neural net, and we can see here the cost function going down. The orange one is the training set, and the blue one is the validation set, which of course is varying more because it's the validation set. But eventually, it's hopefully happy. I'll set it to run for 120 seconds here, but let's stop it now. So now when we have trained a neural net in Mathematica, we can actually use it within System Modeler. So we can, so we generate here a net chain that can, with Create System Model, we put it on as a model that we use within System Modeler itself. So, right. And that takes some time, so I shouldn't have run it, perhaps. And that said, so there you see, so it's coming actually. Let's open again. So here we have a model. I have a missing component, but we can see that we have this neural net that we created, and I can use it with drag and drop as a part of my actual current system. And this I can do in any direction. I can use my system model to train a neural net. I can use a neural net as part of my system model and so on. Hopefully that very quick introduction shows a bit of how system model is. You begin with drag and drop, simulate, get some understanding, and then depending on where you want to go, you can use the Wolfram language to get deep down into validation, for instance, or looking at uncertainties and so on. If you want to learn more, there is a trial, free trial. You got the link for that earlier on also. You can find free courses at Wolfram U and share your thoughts in the Wolfram community. So with this, I'll leave for a couple of minutes of Q&A.
Great. Thank you, Jan, for this informative talk. We have a lot of questions. I will choose the ones which I think would fit in the remaining time that we have. So you mentioned Modelica and FMI. If someone is interested with Modelica and FMI, how can they learn more about it? Do we have any resource that people can use to learn about that?
Right. I think there's a good starting point. Let's see if I can open a web page quickly here. If you don't already have that sort of prepared, but let's see here, Wolfram.com, System Modeler. Oh, what happened? Oh, I can't spell. System Modeler. There you go. And I should remember where to find
these. The resources.
Yeah, right. We can find it on the resources. You know better than I, so that's good. And then
the core components.
Sorry.
The core components section.
Right. Yeah, here you go. So here are basic Modelica, for instance. Let me click on that. And you will get what is Modelica, why should I use it, and from there it will point you all to other resources, including introductory courses and so on. And similarly for FMI and the Wolfram language.
Right. Then the next question was, what did you mean by causal blocks? People think that Modelica is only for acausal blocks. So can you just make that a bit clear?
So Modelica doesn't care what's input and output, which is called acausal block. So we don't care when we do the component, we don't care how we will use it, whether we will apply voltage, current, or voltage to it. That is decided when we actually use the component. However, in many other software, you need to define, this is my input, this is my output. And that's where you do something that is a causal thing that says, okay, this causes that. And this is why FMI or the functional mockup units that you export are causal because they are made so they are able, so you can use them even in tools that do not have this capability of handle acausal systems.
Right. And which version of FMI is currently supported, and when will be supporting FMI 3.0?
Well, currently it's FMI2. We are working on FMI3. There's no date set for that when it will be included, but it will come.
Right.
Right.
I think, Jan, we are like out of time, and we have a lot of questions, which I think we can take in our final Q&A session once all the
And I can
presenters
take
have.
a bit of them in the chat also meanwhile.
Great. Yes, that's great. Yes. Thank you, Jan.
Thank you.
Now we will have Robert Holfquist from Saab Aeronautics and Jörg Sminder from Linköping University. They will share modeling and simulation workflows used in aircraft systems development. The talk will highlight how System Modeler supports architecture exploration, performance analysis, and early stage validation in safety critical environments. So please welcome Robert and Jörg.
Hi. Let's see if we'll see our presentation now. Do you see something?
We are taking a look at your big markers interface.
Hey. See. Window. Share. So let's see. Do you see a presentation or a background?
Aerospace modeling workflows, yes.
Okay, then it worked. Then perfect. So Jörg, are you with me?
Yes, I am. Good morning from the
Perfect.
other side of the Atlantic.
So we have a very distributed presentation here today. I am in Sweden, and Jörg, you are in
Mexico.
Mexico. So hopefully everything works out. But hi everybody. My name is Robert Hellqvist. I'm a technical fellow at Saab Aeronautics within the field of modeling and simulation. Jörg is my colleague. Jörg, do you want to introduce yourself quickly?
Yeah, as Robert said, I'm working as well at Saab as a system engineer.
Yes, and the title of our presentation here today is Aerospace Modeling Workflows for Advanced System Simulation. Hopefully what that means will become clearer throughout the presentation. I will have a set of first slides here to set some context and background and so forth, and then Jörg will talk some about modeling of flight mechanics using Modelica and System Modeler and other tools. So I will start to talk a little bit about modeling and simulation at Saab, why we are using modeling and simulation, past and present. I will use general vehicle systems as an example, as both I and Jörg work with modeling and simulation primarily of general vehicle systems. I will talk some about what I refer to as our distributed approach to modeling and simulation. I will then speak some about our modeling and simulation application development process and provide a connection to FMI and also SSP. Yeah, you heard about FMI in the previous talk, so we'll also introduce this second standard. And then, as I mentioned, Jörg will talk some about modeling of physical systems, and then we'll round off with some summary and conclusions. So Saab Aeronautics is an aircraft developer, and this is something that we have been doing for a very long time. Here you can see some pictures of 3 Saab developed aircraft. We have in the top right, we have the Saab 29 Tunnan or barrel aircraft. In the middle, we have my personal, at least aesthetically, favorite aircraft, the Saab 35 Draken or Dragon. And we have the trainer aircraft, the Saab 105 at the bottom. This Draken aircraft is according to the myth or an anecdote, is that it did not have a top speed. It would simply accelerate until it ran out of fuel. Yeah, so all of these aircraft were undoubtedly very successful in their time. And even though we at our department, we usually brag about having used modeling and simulation since the 60s, we cannot claim that any of these aircraft were actually developed with extensive use of models in the loop. Today, however, we have working on different aircraft. We have the Saab Gripen aircraft in the top here. We have the Global Eye to the right. We have the T-7 Red Hawk aircraft with this red part of the aft fuselage, and then we have whatever is coming next. And here we are using modeling and simulation to a very large extent during development and also during operation. So what is different? Before pointing out what has become different, just using general vehicle systems as an example. So these are general vehicle system of which both I and Jörg work with, are general or aircraft subsystems that are general, that exist in both military and civil aircraft. So cooling systems, hydraulics, fuel system, etc. Nowadays, we classify also propulsion systems as a general vehicle system. Today, they typically consist of both complex hardware and software parts. They are tightly integrated with the aircraft as a whole and highly connected to one another. And each subsystem is designed to solve a number of different tasks. And this is at large one of the reasons why we need to use modeling and simulation during development in order to not only cope with emergent behavior that arise when these different subsystems interact, but also the ability to exploit them to make a better product in a safe way during development. With aircraft, we are not able to test things in the aircraft and fly in the operating conditions where they are intended to use from the get-go. We need to have a safe, representative environment, and their models and simulations become essential. So when using models for development, we adopt a distributed approach. And with that, I mean that the models are developed by the parts of the organization that are responsible for also developing the subsystems. The engineers are spread, developing models can be spread throughout the organization, and they are prompted to use the best suited domain-specific tool at hand to develop their models. We strive to make simulations, models, and simulators available to all engineers that need them throughout all the life cycle phases. And we employ modeling and simulation on an increasing system level throughout development, ranging from component to subsystem to aircraft and systems of systems in the end. Here we have a schematic representation where I put some sort of abstract measure on the vertical axis representing level of integration. So in a sense, how many of the different subsystems that are integrated in the simulation. And on the horizontal axis, we have some abstract representation of time. And here I wrote early phases and late phases. So that does not mean that there are not even later phases here, such as operation. or this is an undefined boundary, I should say. But if we are to work this way, then credibility assessment as an umbrella term becomes essential. So when developing a new aircraft vehicle system, we typically start by modeling the included hardware. And I myself, I am a Modelica proponent, so I would develop this model using Modelica and various different Modelica tools. But as I mentioned earlier, we strive to use the best suited tool for the task at hand. So when developing this model of the hardware, we do a lot of simulations to mature the model and to specify the hardware to be included in the subsystem and so forth. And we use this model for safety assessment, performance analysis, load analysis, etc. And here I try to indicate that we are using the model throughout the life cycle phases. In the late life cycle phases, we heard Jan talk about digital twins, and this would be a potential digital twin prototype in this early phase. So once we feel that we are this model is mature enough, we develop a corresponding controlling software, and we integrate the hardware model together with the software in what we refer to as a small-scale simulator. When I say simulator here, I mean the complete architecture, including the models, but omitting the actual simulation engine, the tool driving the simulation forward in time in case of time domain type simulation. So here we have a small-scale simulator incorporating hardware, the hardware model and the software of a single subsystem model or of a single subsystem. And we use this type of simulator for the same purposes as the hardware model, to develop the models, the software, to do safety assessment, performance analysis, etc. We run a lot of simulations, and once we're mature here, maybe we develop a mid-scale simulator where we incorporate several different closely related subsystem models and their corresponding software. And this we use, for example, for architecture evaluation on a higher system level and a more holistic performance analysis. And lastly, we go to our large-scale simulators. These include most of the model aircraft subsystems. We have an ambition to be flexible here. We have full desktop type large-scale simulators, as well as hardware in the loop simulators. These type of simulators are typically used by pilots and a number of different of the subsystem developers. And they are also shipped as products for training purposes, etc. But in-house at Saab, we use them typically for integration testing, fault analysis, and evaluation of the behavior of the complete aircraft. So with this very distributed approach, we need to have tools, methods, and processes to enable efficient reuse of all the digital artifacts that go into these different simulators. Some of the strengths are that the subject matter experts have direct input on every digital artifact, and all of these subject matter experts are typically dispersed throughout the organization. So this distributed modeling approach is a prerequisite for this to work. Using this ambition to let the engineers work in the best suited domain-specific tool enables an efficient use of human capital, in the sense that a modeler can switch between development projects without having to switch or learn a new tool. So this is also so very important in this approach. As I mentioned, we do need mechanisms for efficient distributed credibility assessment, meaning credibility assessment as an umbrella term, To realize this, we need to use well-established interoperability mechanisms, standards such as Modelica, FMI, and SSP, which I will talk about in a little bit. And we need to have mechanisms to establish and communicate in digital threads. As we are these large-scale simulators or products, we need to be able to declare them as test-worthy. So to make sure that these things are that we are compliant, we have a process for that describes how a modeler should ready a model to be exported for integration in a simulator. This process, called Saab Handbook for Development of Simulation Models, is publicly available at the reference here at the bottom of this page. And at a very coarse level, the handbook describes the steps that you see here in this figure. First, we have a specification activity where we define the purpose of the model. We formulate a verification and validation plan, etc. Then we go into the actual model development, where we connect component models into a subsystem model. We do verification and validation. We get feedback to refine our specification, and once we're ready, we are exporting the model to a central model storage. Once in the central model storage, this model can be integrated in a simulator at whatever level. And at this very coarse way of describing the process, one could express the development of simulators in the same way as well as component models. Yeah, so Jan mentioned FMI. FMI is very important in this workflow. FMI is a result of the EU finance research project Modelica, as far as I know. And basically, FMI specifies a generic format for export of model executables, or so-called functional mockup units. This can be done in a few different ways. FMUs for co-simulation, where a numerical solver is incorporated into the model package, or as FMUs for model exchange, where the solving of the equations is left for the integrating tool. And it provides various means of protecting IP in different ways in terms of source code export, gray box, black box, etc. FMI also provides a standardized interface description in terms of an XML schema. So FMI targets this export step of exporting models for integration in simulators. But we had what I refer to as simulators on various different levels. And that is, for example, or one aspect that the system structure and parameterization standard addresses. So SSP is a portable zip file type format, just like FMI, that contains everything, in quotation marks, that is needed to execute such a simulator. Just to advertise the latest version of standard, SSP 2.0 has been released slightly less than a year ago. This latest version of the standard is primarily intended to keep up and address the FMI 3.0 functionality, but it also provides some nice mechanisms to support incremental development of simulators and architecting. So in SSP, we use 3 of the primary artifacts that SSP specifies. We use the system structure description file format, which captures simulation architecture, how one model is connected causally to another model. The system structure values file format, which is a container for parameter values, and the system structure mappings format, which is a file format that allows you to have customization in the mapping of between values and the model components. Okay, so with that background, I leave the word to you, Jörg.
Yes, thanks very much. You can hear me?
Yes.
Perfect. Well, Robert explained to you a little bit the workflow which we have at Saab in our modeling and simulation development process. I will make now a step back to the very bottom and give you an example for this, how a very component model can look like. For that model, what I will present you, this is a flight mechanic model, which we are at the moment developing. And so the model which we have at the moment is a 2 DOF model. 2 DOF is for 2 degrees of freedom. However, that will be only the start. We are continuing to developing more models, 3 DOF up to 6 DOF. And that's basically for having a certain modularity in the future to choose a model in a adequate complexity for our data simulators. So, like I said, a 2 DOF model at the moment, 6 DOF model will be developed a little bit later on. And these models have as main task actually to provide the simulators and the other subsystems within the simulators with somehow realistic boundary conditions. So if we go forward, please, Robert. Next slide. Yes. So we are working at our department, like I said, like Robert mentioned already, with system simulations. However, what he didn't mention is that our focus is very much also on conceptual design of this subsystems. And here we are working very tight with our colleagues from the aircraft conceptual design department. And why I mentioned this, so they are actually designing, you can say, the outer part, while we are designing the what means this? When we are looking to military aircraft, you see
Jörg, you're cutting. We lost your audio. Can you hear us?
Hello, Jörg.
We are not hearing Jörg, Robert.
That's actually what we try to achieve with this model. So what we are doing is we're building up.
There we go.
Was I away?
We lost you for a little bit, Jörg.
Okay, sorry. So as I said, very short, we are working together with our colleagues from the aircraft conceptual design department, and aircraft conceptual design with the military aircraft design is very much is quite wide. We have different shapes, we have different control systems. So compared to civil aircrafts, we have a much larger variety. So that means also our models have to be more flexible, and by that we need a very modular approach. So if you can please continue with the next slide. So what you see now is actually how the model is basically built up. I will not go into now all the details. So basically the model have like the most flight mechanic models. a flight mechanic component, flight control part, a model for this, an atmospheric model, an engine model, and an aerodynamic model. As I said, there's no time for going into each model in detail, but I will pick out 2 examples which shows you a little bit how we work at Saab, how we share data, and how we integrate, actually, that's what Robert mentioned, how we share models within these simulators. So what you see here is an example for the aerodynamic model. So we have the SSP structure, which Robert explained already, where we can have within this SSP structure different design projects, project A, project B, and all these projects have actually the possibility to take information and models out from this resource file. So our aerodynamic data, in this case, are simulated using a panel code, and this data are at the moment CSV data files, which are then read into 2D tables, which you can find in the standard Modelica library. And this CSV files are then the input, actually, for the aerodynamic modeling. The aerodynamic data are, as I said, an important part for the flight mechanic model, and the flight mechanic model can then saved as an model, point MO model, or directly exported as an FMU for if you want to share it further to other simulators. So like I said, we use in the moment as CSV files. However, we are aiming for the future to apply with more standardized file format, and that's the SSV file. Good. So what we are doing here is, as you can see, we are trying to make use of these Modelica association standards. If you can please continue, Robert. Yes. So here you can actually see that how we can use actually FMUs. So what you see, we have this SSP system structure and parameterization, and so we have the flight mechanic model on the right side. No, on the left side, the other right, and on the right side the engine model. So here, what we have in the moment, it's in the current model is a very, very simplified engine model. However, later we want to have maybe a model which is providing much more precise data, which is more detailed than what we have now. And what we can use here is actually, as you can see, we have the same approach on the engine side. So you can have different engine designs, engine design A and B, and they all use, all these models are using the same structure as we are doing with the flight mechanic model. What you can do is then you can use, for example, the engine file exported as an FMU in our flight mechanic model instead of the current model which we have implemented at the moment. So that's basically the idea, and that is hopefully giving you an idea how we create this modularity and how we want and can share files within this simulator which we're developing. Yes, and to the very left, some very first results, what we get out from the simulator at the moment. Yes, anything to add, Robert?
No, and I think we're a bit. I don't think we have so much time, so I can wrap up with a brief summary. So Our goal with this presentation was to highlight the importance for us of Modelica, FMI, and SSP, and the Modelica tools, of course, supporting all these three standards, such as System Modeler. There are other standards that are very relevant, emerging quickly under the Modelica Association. For example, I mentioned the digital thread, and the SSP LS traceability specification is something that provides really nice mechanisms for this. We see that we can use System Modeler on a number of different system levels. So that is great. And also last, what Jörg showed is a novel, from our perspective at least, and modular approach to modeling and simulation of flight mechanics. And the idea is that we really try to bridge the gap between aerodynamics and systems modeling. And our plan is to successfully verify and expand on this approach in both ongoing and upcoming R&D projects. Thank you. Any questions, if we have time for that?
Thank you, Robert and Jörg. It was inspiring to see how models are used across so many different teams at Saab, enabling collaboration across diverse domains. Yeah, we don't have time, but I had one question that I'm very eager to ask you. Like, what strengths of Modelica do you really find most valuable in your modeling work? If you can have a short answer to that.
What strengths
What strengths of Modelica language do you find most valuable? Like, do you find really nice to have?
Oh, I think one really good thing about Modelica is that it's standardized. We get portable models. That is very important, and we use this fact a lot in daily work, in small things, identifying errors in models, seeing if we get the same results in different tools, and so forth, to learn about our systems and also learn to become better modelers. Very short. Does that answer your question?
Yes, it does.
There are hundreds of good things with Modelica.
Yeah, I know. And for that, we have other talks also lined up. Thank you, Robert and Jörg. Next, we have Martin Nilsson from Nidingen Engineering and Research. Martin will present real-world workflows for modeling, optimizing, and validating thermal management systems for battery electric vehicles. Over to you, Martin.
Thank you. Can you please load my presentation?
Yes, Martin, give me 1 second.
Hello, everybody. I will now speak on the topic of thermal management system design for battery electric vehicles. Does everybody hear me okay?
Yes, we can hear you, Martin. Thank you.
Thank you very much. I can start with saying that, in essence, all models are wrong. There is no perfect model. There is no model detailed enough that it captures everything in reality. And on the other hand, some are useful, as George Box said in 1979. And this is not all bad, because a simple model, purposely built not to contain everything, is often more than its accuracy and level of detail. It's often more than enough. And it often beats a very detailed and complex model, not least when you're debugging it, because trying to calibrate it to data, you will find yourself with the huge model will take days and weeks to calibrate, whereas a simple model will not reach the same level of accuracy, but it's much more nimble, it's faster, and you can work it more. And I'll come back to that. So why does this even matter? Well, I work with thermal systems for battery electric vehicles, of the larger kind, but this is applicable to most vehicles that have a thermal system, or even you can extend it to any thermal system, or actually any system, but I focus on the thermal kind. Also for maybe a building or a vehicle that's not running on the ground. This could be for aircraft, thermal systems, ships, what have you. Doesn't really matter. Modern systems for battery electric vehicles often include heat pumps to save on battery energy. We want to recycle residual heat from various components. For example, the drivetrain contains a lot of heat that we can reuse on a cold day to heat the cabin via the heat pump. So these systems function in a multitude of modes, depending on if it's hot outside, if it's moderate hot, very hot, cold, super cold, around this freezing point, and what do I do with my vehicle? Do I have a heavy load? I'm driving uphill, downhill, so on. So they have to do a lot of things, and as such, they contain a lot of stuff. For example, the system I'm just working on has 7 valves, 4 pumps, 1 electrical fan, 1 heat pump, 1 electrical heater, and the different combinations of settings for all these components, which are 14 in this example. There's so many. You see a small sample on the screen just to show that this is a lot. We really can't do everything like manually. We can't control the system manually. So how do we decide when to use what settings, and how are things ever going to be optimal or optimally operated to preserve as much energy in our battery system as possible? Well, it's no mean feat, because even though it's a simple, we pump around coolant, glycol and water combination in hoses and pipes using standard turbo machinery pumps. The combinations, the sheer number of combinations in the system for their operation, it's enormous. So we have some examples on the screen, which I happily stole from the internet, because if they're public on the internet, I could share them. I thought you have the references there. Here's the Tesla Model 3. This is something from the Schaeffler Group, automotive sub-supplier, on the screen, and this is from a paper. You can see it here if you're interested in it. I didn't read the paper, I just nicked the picture. But you can see here that we have an HVAC unit with a positive temperature coefficient electric heater. We have a blower, we have valves, we have pumps, we have high voltage batteries, we have the powertrain, we have another pump, we have a chiller, fan. There's a lot of stuff, and how to operate these simultaneously, it's a huge question. So what to do? Well, if you look at all these details at once, you quickly become very lost very quickly. One solution is to segment the model buildup, meaning you have different levels of details in your model for different project tasks or phases, meaning, oh, I don't build a model of this particular thermal system for this particular vehicle. I build a family of models which I use, and I use different members of this family for different tasks. Usually the simpler models early, when you have more concepts to develop. Another complementary approach is also to work with large experiment matrices, meaning I use my model's simplicity and speed to my advantage. And then I spiral back. So meaning, instead of, as management theory always goes, is that our development is linear, and then you start with a wide range here, wide scope, and then you go on here. Actually, you do spiral back a lot. You define your things, you design it, test it virtually or in a test rig, and then you go on and take your feedback, you define it again, and then so you spiral back and you see that you actually move backwards in some respects. So there's one logical line going this way, in that logic or in that space, you actually move backwards, but at the same time you move forward along the spiral, which is in another dimension if you want. So you actually move forward along these lines, but in some respects you actually go back. So you can back from my more detailed models. Oh, I have to go back because my test showed me I have to redefine. And then I move along, and then I test again, and see then now you move further along according to both dimensions. So this is how I like to think, that it's no disaster, or it's not a bad thing to actually move backwards in your simulation hierarchy. So how did we do it? Well, we created 2 new fluid libraries because I work with thermal systems. It's a lot of fluids, coolant, liquid, and air, incompressible air in this case. So we don't have to do any fancy stuff for incompressible or for compressible flow, high Mach number fluids. We created 2 libraries. We decided to call them thermofluid and flow. The names are almost arbitrary. We created them from scratch. We had a new interface definition. We created new media models based on the structure that we wanted. I will show you some examples. We created a full set of components. And as a design principle for these libraries, we use limited extents in Modelica. You can extend forever if you want, but we'd have limited extents, and we don't use very many partial models, which goes contrary to the software engineers thing that you should reuse and make maintenance easy and bug fixes only in one place and so on. Since not everybody will be expert users, we created these models from the perspective of ease of understanding and ease of reviewing, rather than so if we introduce a bug, it's possible using this approach it will actually be in multiple places, but most of the code is very similar in each component, so it should be easy to find. But we do that because having an overview of almost the complete model at once actually also helps debugging and introduction to Modelica and ease of understanding, introduction to this library. So that's why we chose that as a guiding principle when we wrote the libraries. We created everything you see on screen. We created components for, and we created icons and everything from scratch. So the connector we did in the flow library, the thermofluid, I will not show because it's almost duplicate. The difference between the 2 libraries, if I move back, is that this deals with energy balances, heat flows and energy flows, but does not do any hydraulic calculations. If you're interested in pressure drop and flow balances and stuff, you will have to use this. In this library, which is used for conceptual development, you will have to, in each branch of the system, define your flow, volume flow or mass flow, it's your choice, explicitly. So I use this a lot for concept development, but then when I design my system, I go to this one. I will come back to this eventually. So we had a fluid port. You have to have a flow variable. We chose mass flow. We have a potential variable. Pressure is an obvious choice in fluid systems. We have 2 stream variables. We use enthalpy and we use a mass fraction x. But in all practicality, you can use x. X can be almost whatever, depending on how you write your media model. The media model is written according to this principle. We created first a template, and all functions have a name like property, underscore, and these are the input variables. And for the flow library, we take pressure, temperature, and the variable x as input. If we use them or not, that's really not the question here. That's what each function needs to work. And then we create a template, and then we extend that template. And for liquids, we typically populate it directly with equations for the fluid properties. In our case, different versions of ethylene glycol, Some of them are hard-coded, doesn't use X because they're hard-coded for a certain glycol concentration. Some have X as an input, and then you can vary very easily without changing the media. You can vary the glycol concentration. For ideal gases, we did a little different approach because a lot of gases you can use the same set of state equations and just change the coefficients. For example, when you define viscosity, you use Sutherland's law, and they have the same type of coefficients regardless of the gas, if it's nitrogen or air or hydrogen, for example. Same thing with if you use a variable CP, you can use the NASA-Glenn coefficients, often called the Berkeley coefficients or polynomials. You can download a set of those for many different gases from the web and implement that. So that's how we did it for gases. It's just more practical because those libraries are already there. It doesn't really exist for different coolants. So there we implement them directly. Then we build a conceptual model. The example shown here is not really, it's a lot simplified from what we would have in a vehicle, because here we have a radiator in the simplified thermal fluid library, which is yellow. I call it the yellow library. We don't have a pressure drop or anything, so we don't have a fan to drive the flow through the radiator, so that's explicitly input. We have a sub-circuit here for something we can say it's the battery. Have a heat pump or a refrigeration system with a refrigerant. Not modeled, we model its behavior, not its internals. Then we have two branches of coolant going to the drivetrain, my little drivetrain model. One for the gearbox and one for the motor inverter combination. And then this little drivetrain pushes on our vehicle model, and then some controls into that, and then we can drive this. We can define a drive profile here, so we can drive from A to B. As it happens, I'll show you some results later. So this is the library where I mentioned we have energy balances and heat flow only. We would have to, you can see here, I put in my pump icon, I actually put in explicitly what my mass flow should be, and also in the sub-circuit here. And then I explicitly define in this, I use a valve icon, but it's actually a flow splitter telling 0.7, the fraction 0.7 of this flow here goes in this branch, and then 30% goes here. I explicitly define that in this library. Oh, what happened? Okay, back again. Not sure what happened there. So I typically use this library and this type of detail in models to evaluate many concepts, and this can be used to create a first conceptual design of a control system. This conceptual model I ran in a drive cycle, because I have a drivetrain and a vehicle model, so I can evaluate in a drive cycle. It does require that I first created a conceptual control system, because otherwise my thermal system won't work. Without the control system, it will work in manual mode or steady state modes only. So before we actually do the drive cycle, we create a large test matrix with thousands of points, and then we do something called a system characterization, or I create data and hand it over to my control system team members, who use that to perform a system characterization, often using Simulink, who has tools for this, and not in Modelica. And then from that, they define a control system. They define the system from the control system point of view, or we decide to do a hybrid approach and maybe use this data to train an ML algorithm. We did show in an advanced engineering program last year together with Wolfram that it was possible actually to train, with using data from these models exclusively, to train an ML without any different control functions, just an ML algorithm, a neural net created in Mathematica, to control one of these systems over a 4-hour drive cycle in for various times of the year, meaning different ambient temperatures. And then once we've done that, we model the system again using the other library, the flow library, where I showed you the connector and the media model. And we include hydraulics. So this allows us to actually design the hydraulic circuit. We can select component. We can use this as a guide in selecting components, pumps, fans. We can size the heat pump, hose and pipe diameters and lengths. We design the system hydraulically. And at the same time, we continue with the next step in the control system development, because at this stage, we add more functionality, we add more detail, so the control system designs need to be fine-tuned. Once we have rig testing, meaning data from the real world, can be scary, but we use that data to calibrate these models to see that our pressure losses and flow balances are correct, our thermal masses are adequately represented, and then we can calibrate the control system again. And the reason we do that in steps is that typically, historically, you would design your system, then you would design your control system as a side activity. These come together first time in the vehicle, and then you spend months calibrating and fixing things on the software in the vehicle, which is very expensive and also not very practical, because you only have the vehicle very late in the development process. So now we can do it way before, years before we actually have a vehicle, to find bugs and things we haven't thought of, which we always do early. So to wrap things up, to provide a couple of minutes for questions. No model is perfect. So we utilize a stepwise approach, a tiered approach if you want, where we add detail as we go along and as we go back and forth. You can see it as a pendulum or as a spiral in my view. So first, to down select concepts, we run huge DOEs, tens of thousands of cases. We haven't really gotten to the tens of thousands yet, but maybe 1,000. It's where we've gotten so far. We're developing a new workflow as well. To do system characterization, train algorithms, or something else. And we add detail as we go. And then we start all over. Thank you very much. I'm ready for questions if you are on the Wolfram side.
Thank you, Martin. That was a very interesting presentation. We have a question why did you make a difference between energy flow and heat flow in your slide?
I think that was just a wording thing. What I convect in the if you mean in the yellow library, or actually the green one as well, the flow library, what's being transported is enthalpy.
Right.
And energy can be heat, if you put it that way.
Right. So Martin, you have two different libraries, like the flow library and the thermofluid library. What's the need of two libraries? Couldn't you just use one, or what's the difference between the two libraries that you have?
Well, the difference is the hydraulics mainly. And since I don't have to worry about the hydraulic, the pressure losses, there's a lot of geometrical stuff I don't need to know when using the thermofluid, the yellow library. I don't need to know my pump curves. I don't need to know my fan curves. I don't need to know my pressure drop in my radiator. I don't need to know my hose diameter to be able to have the pipe pressure losses in the hoses and pipes. I don't need to have the electrical drivetrain. I don't need to know everything about the flow, the coolant passages in the electric motor, in the gearbox, and so on. So I can do a lot of thermal analysis without having information about that, because these components might not exist. But I know from experience that, in a large heavy-duty vehicle, we usually have 100 liters per minute in this part of the circuit. I have 25 liters per minute in this part of the circuit, and then I can just design that and go along with my thermal balances, I usually call it, and then I can start with my colleagues who are responsible for the control system development. They can start thinking about strategies to control it, to optimize the system, in order to minimize energy consumption of the thermal system while performing its task of keeping the battery between 22 and 28 degrees, and the cabin around the 22 mark. already very, very early. So that's, I don't, there's a lot of, in the simpler library, there's a lot of stuff, information I don't need, which allows me to start much earlier than I otherwise would have been able to do.
Right.
And I think that's a key thing, right? That which I pointed out in mine. You started your presentation with that. All models are wrong, but if used adequately, and that's what you found, that for some purposes you need something simpler, and then you have the simpler, and for some purposes you need something more advanced, and then you have that more advanced for that.
I compensate. I use the simpler model, and I compensate for the lack of detail with huge sensitivity studies, design of experiment matrices, because I could have added more detail and get more closer, but in doing so, or avoiding that, because I have uncertainty in my model, because it's simple, I run it multiple times, varying different inputs, and then I can easily see, and I get a mathematical statistical proof that my system will behave within the bounds I want. So I can actually compensate, or more than compensate, for it, for the model's lack of detail. When I move to a more detailed model, I can do the same, but since the model is more computationally intensive, I maybe can't afford to do 10,000. I can maybe only do 1,000. So I need to have had a down select of something before, because I can no longer afford to run 10,000 cases. So I have to run fewer parameters in my, or fewer variables in my design experiment matrix with the more detailed model. So that's why it's not a bad idea to do a much larger matrix, because I want to have a statistical data set, so I can base my statistics. The data set is there, but I can base my findings of the system on statistics based on a large number of samples. Just the larger number of samples, the more sure you are, right?
Yeah.
Right. So Martin, you have so when you created this library, how long did it take? We have a question. How long did it take you to develop these libraries?
Quite long, but shorter than you might have imagined. I did not use any AI tools to create them, because at the time, which was not very long ago, about 12 to 18 months ago, I could not, ChatGPT or Claude or whatever, they weren't good enough, so they didn't contribute almost anything. But it was me, single-handedly, about half time, and one well-known consultant at Wolfram who wrote this together with me in a little project we had. The well-known consultant is in the armchair there in the green shirt.
Okay, fine.
And we did it together. I did maybe 2/3 of the work, and Ankit did about 1/3 of the work, mostly on the yellow library, which we developed first. But I wanted to do this for years, because I never found the MSL, fluid, and media libraries, A, to my liking, B, being very easy to use. Definitely not for somebody who's a beginner to Modelica, because they're almost impenetrable, especially the media library, to trying to figure out where actually things are getting done. And it lacked a lot of stuff that I wanted. So basically, my inner control freak told me I need to do this by myself. If you want it right, to do it right.
Yeah. One final question, Martin. Like, when you create these libraries from scratch, what key principles did you follow in your library development process? Something for our audience to just get insights from.
Spend a lot of time on thinking about your interface, because if that's the first stone in your wall that you're building a wall or a house, that's the first ground stone. Your interface, think of that thoroughly. You will have to redo it many times. We did. The media model, because any fluid models, component models are built on that, because they all use it. So that's what to do next. And do a long and hard think about that, to make it simple, easy to use, easy to expand, easy to add new media. And then after that, as I said before, I personally use a limited set of extends, so I have most of the stuff visible in the text view. Do nice icons, so that this library is fun and easy to use, and things are clear. So spend a lot of time on your icons to make it usable. That includes selection of color, so that you don't have ended up with a boring palette. I got a lot of feedback on that, so I changed my palette several times. That's basically that, and then don't overdo it. I reduced the scope really, so this only does single face, single species, and you can add some pseudo changing media via this magical property X, which can be concentration, for example, in a glycol water mixture. So don't overdo it. Don't think you can do two-phase change and everything. Make a separate library for that. So keep things simple. Simple is fun.
Right. Thank you, Martin, for this wonderful insights. Right. So yeah, our next speakers are Alexandre de Cornier and Pedro Fonseca from Suez Engineering and Construction, who will discuss simulation-based design and optimization of hydraulic and energy performance in large water plant pipe networks, and how coupling Wolfram System Modeler with Wolfram Language enables powerful optimization workflows. So over to you, Alexandre and Pedro.
Hello. Hello, everybody. I'm Alexander Le Corner from Suez. I'm a hydraulic engineer.
And I'm Pedro Fonseca, head of the hydraulic department at Suez.
Okay, and we will tell you about how we use Wolfram System Modeler to optimize our pipes and pumps because we do design and build water plants, wastewater plant, as well as drinking water plants and desalination plants. So we do have a lot of pipes and pumps and water tanks to design. Okay. So we'll take a simple case. We will have a low tank that is receiving a flow coming from a sewage network, so wastewater flow, very variable, of course. And we want to bring it to a wastewater plant, which is located higher. But we don't want to bring the whole flow there. We want to bring up to 2.2 cubic meter per second. And the excess flow, which happens usually during rain, we will send it to another treatment, which is a bit lower. For this, obviously, we need some pumps to lift the water. We need some pipe. We need a pipe network. You see, we made here a long pipe, 2.5 kilometer, and some short pipes here. And we need something here. We don't want most of the time we want these circuits to be closed. Only when there is the rain peak flow, we have water flowing through this circuit. So we need a control valve. At this stage, it looks obviously like a Modelica system modeler diagram, and it is eventually. At this stage, it's not real pumps, not real valves, it's just ideal flow sources. Okay, so we have, I would say, a kind of architecture, but not a design yet. And Pedro will tell you more.
So with these simulations, we can address one of the most critical design decisions in water conveyance, that is the selection of optimal pipe diameter, pumps, etc. And this decision is inherently multi-objective because, well, it's a balance of competing criteria like hydraulic performance, construction costs, environmental footprint. For instance, in hydraulic performance, if pipes are undersized, well, head losses increase, discharge pressure at the pumps rises, energy consumption grows. On the construction costs, well, on this particular project, part of the pipeline will be built using micro-tunneling, as we can see on the picture above, yes, which has a very high unit cost, yes. And on an environmental footprint, well, certain sections cross sensitive or complex areas, which increases both construction costs and CO2 emissions by consequence, yes. So all these variables, together with the minimum velocity constraint required to ensure transport of settable solids, become part of the optimization vector used to determine the most suitable pipe diameter, yes. Now, the key input is the flow distribution over time. We can see on the left side. The system operates most of the year at low flow rate, occasionally medium flow, only a few days per year, peak flow. Well, designing the system to be optimal only for peak flow, well, obviously leads to inefficient solution for most of the operation conditions. And so our goal is therefore to find pipe diameter that optimizes total life cycle cost, emissions, and for the main operation condition regime. On the next slide, talking about multiple objective optimization with System Modeler. To select the optimal diameter, considering all these inputs, we use System Model coupled with Mathematica. The model includes a time-dependent flow table that we already saw it there as an object, which represents the long-term flow distribution. Yes, this flow profile feeds both the pumps and the control valve that was mentioned previously. We then load the simulation into Mathematica to run the model thousands of times using an automated optimization workflow. The objective function minimizes TOTEX, and this includes CAPEX, well, construction costs, OPEX, operational costs in mostly energy consumption, and CO2 footprint, yes. So this is a multi-objective optimization problem solved through parametric sweeps and search algorithms that converge towards kind of a Pareto optimal solution. The resulting optimal design is well, it's kind of obvious and at the same time interesting. The long micro-tunneling pipeline on this example converges to a small diameter because of the construction costs. And on the other sections, the lower differential cost converges to a larger diameter to reduce energy consumption, yes. And so it kind of finds the balance on a expected way on this example. Moving forward.
Okay, so now we have a pipe network with diameters. So we know the total head we need on the pumps, well, the discharge pressure, because we have the networks, and we typically receive several offers from pump manufacturers, and we have to select a pump model. The manufacturers typically they send us this type of curves. It's the first one is showing the flow, the total head, the pressure versus the flow. There are efficiency curves. All these curves are at nominal rotation speed for the pump, and quite often, most of the time, we operate this pump at variable speed. So we have the possibility with System Modeler and our library to operate this pump at variable speed, and there are some rules to modify this curve according to the speed. And we can do a very simple model with the pump model. First we run one pump from 0 RPM to max RPM. We reach something like 6,000 cubic meter per hour. This is the flow. And this is the efficiency, meaning it's the ratio between the shaft power we inject in the pump and the hydraulic power that is restituted to the system. So the efficiency at the beginning is not good. This is the good zone, 0.8 and even higher, and this is not a great zone. With two pumps, we get a higher flow and the efficiency curve is like that. But here we'd better switch to 3 pumps. And here we'd better switch to 4 pumps because we want to stay always on the best possible efficiency to spend as less electricity as possible. So with a simple simulation, we can get a quick overview of what we could get this dashed line with this pump model, and we can easily compare different models. That's very simple and very efficient. So now we have a pump model. It's quite okay. We are quite happy with this efficiency.
So, well, after selecting pumps and pipe diameters, it is typical to perform transient analysis on the system. So we kind of simulated critical scenario, typically all pumps running at full speed and a sudden stop due to power failure. For the purpose of this presentation, we use a simplified rigid column model, not an elastic pipe behavior. But we do include pump inertia, motor inertia, behavior. Well, the pump at a given moment becomes a dissipative element after shutdown. The results, well, we can see it on the screen. The results show that immediately after power loss, pressure downstream the pumps, that is at that pipe's signal in red, drops rapidly from 6 bars approximately to subatmospheric pressure. This occurs because, well, the 2.5 kilometers of water column that is going forward along the pipeline has a strong inertia. And so water continues moving while the stop pumps becomes a restriction in the system, yes. This can lead to a pipe collapse. Unfortunately, it does happen. Pipelines are quite robust against pressure from inside to out. But, well, when we submit it to negative pressure, it's quite easier to implode them, yes. And so this is a major risk that we must mitigate, yes. On next slide, so we can see that we added a vessel on top of the model, a pressure vessel. So this vessel acts as a reservoir with compressed air inside, acting as a cushion. And so it provides flexibility during the shutdown. When power drops and pumps rapidly lose their ability to supply flow, the vessel temporarily supplies water to the network. Yes, the expanding air maintains pressure within safe limits. We can see on the plots that around 600 seconds, we clearly observe the transition between pump supply to vessel supply. And so we can see that the pump supply rapidly drops at the exact moment where the vessel starts supplying water to the system. Yes. At the same time, we can see the air expansion progressively reduces pressure on flow, but this is controlled on a gradual manner. So we can see the flow rate going down slowly, yes, avoiding a sudden depressurization of the system, yes. The vessel behavior on the first plot can be, well, we can see that the liquid level decreases as water is supplied, yes, and then the system reverses and the vessel refills again. Well, this is a cyclic movement after the pump stop. We can also observe that the vessel is correctly sized because we can see that the vessel never empties. Well, it's represented by the orange zero line, yes, there. And at the same time, on the lower plot, where that is representing what we were seeing on the previous slide, we can see that now pressure no longer goes to subatmospheric pressure; it remains above zero. Yes, well, with this hydraulic design completed, we then move to the control architecture, and that will be Alexander continuing.
Thank you, Pedro. So to complete our system, obviously we need a control, and for this system, the basic thing, we want to keep the load tank at more or less constant level. We don't want it to overflow on the roads, and we don't want it to be drained because we cannot pump anymore. So quite logically, we have a level set point for this tank. We have a level measure, and we feed a PI controller that accelerate or slow down the pump. You can see on this diagram that we do not have the 4 pumps of our system, but in fact we have some flow division and flow multipliers, and we can send to these components a value which can be 1, 2, 3, or 4. If it's 4, it's like a pumping station with 4 pumps, in fact. But we simulate only 1 pump to have a lighter simulation for a very similar results. This block is in fact just starting another pump or stopping a pump depending on the speed of the pump in operation. And very quickly we can see the reaction of the system over a quite long period, and we can simulate 20 days very quickly in 1 minute. I can show actually just at the end of the presentation during the question the real simulation, and we can quickly identify issues. Here we have an issue. We have multiple start and stop of the pumps within a very short time, and we don't like that at all. And it's very easy to understand, analyze, and to solve these issues. If I had been on site, I would need to stay on site several days to see the issue happening. Then I would try another setting. I would need to stay again several days to check if the result is okay. So there's obviously a strong interest for us to use this tool. And things we do also still with Mathematica, we can do also automatic optimization of control parameters. With Mathematica, we give a target to Mathematica for a variable. It could typically be amplitudes of oscillation to minimize, or overshoots, or number of start and stop of pumps, etc. Or a composite variable that takes into account all these factors. So that's part of the things we do with a System Modeler, and we can really, well, we started something like 2 years ago with little things, and now we can really use it on real cases and with great benefits. Okay, that's the end of our presentation. If you have any question, we can answer, of course. And
Yes. Thank you, Alexander and Pedro. It was a very informative talk. So if I understand correctly, you created the library from scratch, right?
Yes, correct. Yes.
So I have the same question for you as I had for Martin. What key principles did you follow in your library development journey?
How to answer this question? We tried to use Modelica standard libraries for 2 or 3 days, and with no knowledge at all of Modelica. And after 3 or 4 days, I was nowhere. I couldn't do anything with the fluid library of Modelica. I could do things with the electrical library, which I do understand. Well, not all, but so after 4 days, I started to create my own library with small things. It did work. not great, but we could simulate an interesting project, and that was the beginning. And then we developed more and more components. At some points, the library was a big mess, so we had to restructure it. So it's, and we are still working a lot on this library to make it more stable, to make it more user friendly. It's a continuous work.
Right. Can I comment on that? I think what you said here is so we see here the fluid library, same as Martin, is that it's an advanced library. Then there are the rest of the, say, MSL libraries are typically much easier to use than the fluid library. But that comes from fluid systems having so many ways of wanting to do stuff in many times. So I'm sure if we compare your library with Martin's library, they're quite different because you have different needs.
Sure.
And I think that's part of it. And you're also showing there, saying that what you did is you started with some simple model of something, and then it evolved from there. And I think that's a very common way of how you actually do, because then you really learn from the basics, from the ground up, and then at some point you come to the decision, now it's actually time to break this down and do it really nicely, well structured, and get a library that is perfect for our needs.
Right. We have a question from Martin. What variables did you use for the interface in your library, like in the connectors?
So at the interface, our we call it head library. We use total head in meter, which is kind of pressure, but expressed in meter of water column. It's the level of the water in a transparent tube that would be connected to the pipe. So it's the altimetry of the water in the pipe or the reservoir. And actually, we did use the volume flow, not the mass flow. It's not correct at all in terms of physics. But for our applications, that's what we use, and that's really fine. So, and also we have another library where we use streams also for process things with suspended solids, salinity, etc. And we have some more components with that you on this library actually. That's basically
that was a
what
really good example, by the way, of you and of the thing of you have so different viewpoints on the same thing. For you, it makes sense to have meters. For Martin, for sure, it doesn't. When his when his vehicle goes uphill, meters would not be very good.
Okay, so I have a follow-up question for Martin as well. What about the media model you guys are using in this library? Do you use any media model?
No, we don't use any media model actually, because when I developed it, I really had difficulties to understand how this media model was working. So I made it's basically water that we use in water industry. So it's water. We can adjust salinities, temperature. The viscosities are of course updated according to these, and the volumic mass are updated according to these properties. And I would say that's fine for what we do. So our media is water. But yeah, basically yes. We use gas a little bit, but on specific cases.
Right. So there was a question from Andrew. Did you say that you could troubleshoot by matching plots to failed components in the system model? If so, is there a machine learning technique to match curve forms from real sensors to system simulations?
We did not try that at all yet. It would be interesting actually. These days, I would say we are designing plants with these systems. These plants will be built, but it always takes time. It takes several years for this project to be built and commissioned. And in a few years, it will be very interesting to compare if what we did during engineering phase does match the reality of the site and recalibrate things. But at that stage, we did not do that yet.
Right. And which criteria did you use to place your surge tank on the right of the pipes or to the left?
Well, we want this. Pedro, maybe you can answer this question.
Yeah, I was writing it. Yeah, I was typing it right now. I mean, the location, if you mean the location, it's common engineering knowledge from water hammer transient analysis that we should continue the supply of water the closest possible of the point where there has been a shortage of water. So in this sense, it's to approach the vessel to the pumps that are the elements that change their condition upon power failure. If we place it further away, we are going to have the phenomena developing until it finds the vessel, and so we end up with two oscillation systems, one upstream the vessel and another one downstream the vessel. I don't know if this was the question.
Right. Right. Thank you, Pedro. You seem to use the integration between System Modeler and Wolfram Language quite heavily. Could you elaborate a bit on how that integration has been helpful? I know you mentioned optimization, but in general, how has the integration been helpful in your workflows?
You want to answer this question, Pedro?
Yeah, sure. So we often develop a model that can be later on seen as a black box to the user, or let's say to the end user, and then the end user explores it with Mathematica. It can go from simple swap of parameters, multiple parameters, until there's an optimum or a failure case that is found, or we can actually implement some more sophisticated let's say optimization algorithms to calibrate the outcomes to a existing curve, for instance. It's one of the answers I gave to the question: do we couple it with real data from site? Well, it's easy to couple it with real data from site by using Mathematica as the intermediate actor, trying to let's say optimize parameters until we get an answer similar to the site. Yes, it brings flexibility to the workflow, basically.
So in a sense, you're could I put it like this, that you are using notebooks as playgrounds for other users?
Yes, well, other users. Yeah, the community is very restricted, so we are not having a lot of multiple users. But yes, it opens the possibility of, as you said, use it as a playground to operate on the models as let's say as a power user.
Right. I had a thought you could easily use Wolfram Language to identify some thresholds. I see your plots, it has so many fluctuations, and if you want to automatically identify which set of parameters are within a threshold and which parameters are going out, so that you could easily find those scenarios. Do you use some kind of workflows for that to automate validation of your systems?
We did most of the time. Actually, we look at the plots and we find quite quickly the issues. But we did things where we wanted to have an automatic optimization with Mathematica. And then, of course, we need to define a variable that represents the bad thing. So this variable is typically an amplitude of oscillations or anything. Well, we have to quantify this thing we don't want to ask Mathematica to minimize it, working on all the parameters. So to answer your question, finally, yes, for some models we did calculate several indicators of things we didn't want to have with a magnitude and a final composite indicator which did represent with some coefficients how bad was the situation. And the goal was to minimize this indicator.
Right.
And
thank you.
It's fluctuating a lot because the wastewater flow is always fluctuating with events in the cities.
Yes. Okay. Thank you, Alexander and Pedro. It was very informative talk, and thank you for your insights. Right. So now we move on. Next, we have Robert Frinswright and Konstantinos Antoniadis from Berkeley and Imperial. They will demonstrate how they build operational digital twins connected to real equipment using System Modeler and OPC UA. Over to you, Robert and Konstantinos.
Hello there. I'm just sort of popping up on the screen to say hello. I'm going to close down the camera just to maximize my bandwidth. So, hello from Houston. Thanks all for joining us today. I'm Robert and delighted to be presented alongside my colleague Konstantinos. We have a personal connection to the image that you can see on the screen as we occasionally work with people who were directly involved in the incident on that day. So we're pleased to share our work here today on a topic that's critical to safer and more efficient drilling operations in challenging environments like deepwater drilling. Today's presentation is titled Preventing the Next Blowout, Digital Twins for Managed Pressure Drilling Hydraulic Control Units. I'll explain what some of these terms mean in the presentation. So, Deepwater Horizon was a defining moment for the oil and gas industry. In 2010, the oil and gas industry caused the largest marine oil spill in history, a catastrophic blowout that resulted in the loss of $1 billion drilling rig and a foreign explosion that killed 11 workers. Total financial costs exceeded $65 billion and shaped the future of the drilling industry. The industry response was to promote the use of best available, safest technology. BAST is a test to ensure the most advanced, effective, and safest technology option is chosen by drilling companies and suppliers, all within the constraints of practicability and economics. So BAST assessment had identified managed pressure drilling as a promising technology. It creates a closed loop mud system that allows pressure management and early kick and loss detection. So what we can see in the diagram as the red box appears is what we mean by closed loop. So conventional drilling, as represented on this diagram, has mud pumps pumping through a standpipe, down the drill pipe, back up the well with the cuttings, out through a flow paddle, the rig flow line, onto the shakers where they remove the cuttings, and then back to an active mud tank, and from there it goes back round in a circle. The key thing to note here is that the well is actually open to atmosphere, and that was the reason for the blowout that occurred on the Deepwater Horizon. When we close the loop, we introduce a barrier at the top of the well, preventing blowout at the rig floor. But we have to then take returns through what's referred to as the managed pressure drilling system. So it's a set of valves and chokes that provide back pressure to the well that allow us to control the pressure along the well bore and also detect kicks and losses while we're drilling. So the hydraulic barrier becomes safety critical, and it's maintained in place by hydraulic control system. So conventional quality management systems are built on the notion of verification and validation. Those two terms are often interchanged, but there is a sort of a clear way of understanding them. BNI's role is to demonstrate that each MPD system fulfills the requirement for functionality, fault tolerance, and reliability. Traditionally, we've used system safety engineering tools like hazards and operability, and failure modes and effects analysis to demonstrate control of hazards. Now, these tools have highlighted some hydraulic functions utilized by an MPD system are operability and safety critical. So the challenge to us at BNI from the industry was whether we could combine our traditional system safety engineering expertise with our nascent digital twin expertise. This led us to evaluate whether Wolfram technologies can provide key elements of the technology stack for delivering a product. The BNI verification solution has three essential pillars. First, conduct detailed failure modes and effects analysis to ensure we understand the system before modeling and simulation. This is to ensure we fully understand how the system works and make sure that the model is representative at the right level of fidelity. Second, simulate system states to confirm functional completeness. So this step is around making sure that the model can actually replicate all the different states that the system can be in, both fault and also, normal operating and also fault states. And then third, we conduct fault injection analysis to validate fault tolerance at the level of components and subcomponents. And that involves us basically injecting faults into the running simulation and then observing the behavior of the system afterwards. Our final goal, to be completed in 2026, is to define failure rates at the component level in order to determine the effects of faults on the top level safety functions. Now, I'll explain some of what you saw in the diagrams there. Some of it we had to anonymize because the hydraulic system itself is actually confidential. To build these pillars, BNI created a Wolfram language application to control a virtual system simulation created in System Modeler. To achieve this, an MO file is imported into a notebook, then simulated, and then faults are injected under the control of Dynamic. Results are written to notebooks that are then saved as timestamped PDFs to provide us with document control for change management, which is of course essential for maintaining class society approval under the national regulatory frameworks. We've also created a notebook animation of the hydraulic circuits using graphics primitives. It allows us to play or step forwards and step backwards through time, thereby giving us the chance to interrogate the model at a deep level, both visually and also using palettes and notebooks. The BNI validation solution led us to what we believe is a novel and important concept using digital twin instances. The ISO definition of validation can be boiled down to the question, how do we know the system fulfills its intended function? i.e., does the system do what it is supposed to do? Validation is normally conducted by review, factory acceptance testing, systems integration testing, and commissioning. But what if we could extend validation into real-time operations? We therefore built our service around the notion of simulation for verification and Sentry for validation. Both use the same basic virtual system simulation, but this time the Sentry is connected to the actual thing, allowing us to real-time validate, which of course changes the paradigm. In BNI simulation mode, we use the standalone VSS. It enables us to conduct design iteration, performance optimization, time-stamped fault injection, reliability and sensitivity studies. And in addition, it supports operator training and real-time diagnostics. In BNI Sentry mode, we use a modified version of the standalone virtual system simulation. Synchronization is achieved by embedding a Wolfram OPC UA client in the VSS, which allows us to ingest live data like valve positions, pump speeds, pressures, and so on into the model. And it allows us, or the operator, to conduct real-time validation, for example, by comparing actual sensor data with our digital twin predictions. This means we can detect and alarm anomalies in seconds, both locally at the rig and also in a real-time operations center. So the challenge is, could BNI build a technology stack capable of meeting the following requirements? We need to do parameter synchronization of valve positions, pump speeds, and so on. System state representation. It must allow us to simulate nominal and fault states. It should visualize the hydraulics and mechatronics using 2D animations, allow bidirectional simulation communication, analyze system performance and auto-report when deviations occur, and it must generate actionable insights. We must also be able to deploy multiple instances in parallel on our client's network. And finally, we need to aggregate, analyze, and visualize fleet-wide big data from the simulations and from the actual systems. So up to now, I've described what's required, but the next few slides presented by Konstantinos explain how we developed and delivered a client-facing solution that will be deployed either as a Dockerized product installed on the client's network or perhaps as software as a service. We combined Wolfram Language System Modeler and complementary engineering tools like .NET into a commercial-grade digital twin platform where Wolfram Language sits on top as the orchestration and analytics layer, handling automation, fault injection, reliability calculations, reporting, and parameter studies. The outcome, we believe, is safer operations, reduced risk, and more sustainable drilling practice. So I'm going to hand over now to Konstantinos.
Thanks, Robert. In this slide, we are going to describe the core engineering workflow behind the digital twin implementation, with one major constraint in mind: the model must run in real time. Real-time capability is a fundamental requirement of a digital twin that affects modeling decisions, level of detail, solver configuration, and of course, initialization strategy. We start with building a physics-based model of the hydraulic control system. This model must be computationally efficient and numerically stable when operating in simulation and sentry modes. To verify the model meets the requirements, we validated simulation results against system integration tests for normal operating scenarios. After understanding the failure behavior, we performed optimization and calibration. We adjust parameters, test sensitivity, and evaluate how robust the system is against uncertainty. Our ultimate goal is to use the new tunability analysis framework in FMI. We have found that a critical step is initialization. The model must start from a steady-state condition with no artificial dynamics. This systematic approach to build, simulate, verify, optimize, and calibrate transforms a model into a safety assurance tool. Now we're going to see the architectural foundation of our solution. A digital twin in a safety-critical offshore environment must communicate reliably, instantiate more than once, and remain cyber-secure. At the core of the architecture are structured APIs that connect simulation, live equipment, data storage, and visualization. The physics-based model runs in System Modeler. Communication with the simulation layer is handled through a .NET client over TCP. This ensures a deterministic control interaction with the model. In parallel, another .NET client manages OPC UA communication. OPC UA is essential here since it provides a secure, standardized ingestion of live operational data such as pressure, pump speed, and valve position. Above these layers, a .NET server application sits. This acts as an orchestrator. It instantiates simulation instances, manages execution cycles, and controls synchronization. This is what allows us to deploy multiple twins in parallel. After I describe the architecture and the integration, this is what the end user will see, the user interface. The digital twin runs simultaneously with the actual hydraulic equipment. It receives live data like pressures, valve positions, pump speed, and continuously calculates what the system should be doing according to physics and control logic. In other words, it acts as a real-time sentry of the physical system. When they begin to diverge, even slightly, the digital sentry detects the deviation immediately. In parallel, we have live dashboards providing analytical insights, trends, and statistical deviations. The final step now is deployment. A digital twin is valuable only if it can run reliably in an operational environment, not just in a development machine. For this reason, we deploy the platform using a Docker container. The twin runs the same way in development, testing, and production. No dependency conflicts, no configuration drift. From an operational standpoint, Docker enables scalability. We can deploy multiple instances per well, per rig, or fleet-wide. In Sentry mode, the containerized twin runs continuously alongside the real equipment. It ingests live data, computes expected behavior in real time, and triggers alert when the deviations exceed defined thresholds. Because it's containerized, it can be deployed offshore on the rig and or onshore in a real-time operation center. Now, Robert is going to summarize all of what we have done.
Thanks, Konstantinos. So to conclude, the question that we had when we started this, which was a couple of years ago, would Wolfram products deliver what we need for a client-facing product? And the answer, we believe, is an emphatic yes. And we can deliver, or have delivered, a real-time virtual system simulation and digital twin for simple, or for a simple and moderately complicated hydraulic control system. The graphic at the end here, it's we're jumping around at the moment, but the last slide, if we go to slide 17, is a simplification of the Digital Twin Consortium's technology hamburger, as they call it. So if we could stop at 17. Yeah, so use your imagination, you can see a hamburger there. So what we've shown is communication can occur with external data sources. Virtual representations can be built in System Modeler and Mathematica. Wolfram's OPC UA and TCP IP can be used for synchronization and communication. Data is made interoperable by the use of the OPC UA standard. We also have security, trust, and governance provided by OPC UA communications. And the IoT platform allows us to Dockerize, instantiate, and aggregate the results. So going forward, we intend to extend our applications of this technology stack to include more of the drilling services and a more complex subsystem and system. This will lead us to explore how we use FMUs in co-simulation to represent the whole drilling system. So one of the things of interest for us today is to hear from others if they have experience in this regards, so that we can exchange ideas. So that's everything that we have. Any questions?
Thank you, Robert and Konstantinos. Just a note for our audience, like OPC UA that Robert, you mentioned, is one of the free libraries that you can find in our library store. So it's basically, it has components that use the OPC standard and that you can use to communicate with external devices and applications. So Robert, like you use the integration of Wolfram Language and System Modeler a lot in your workflows. Can you pinpoint like what are the different workflows where you find the integration really helpful?
Well, I think one of the key things is that, as you can see on the hamburger, we're not just using Wolfram technologies. What we have is an interface into, as you can see, external data sources, Internet of Things, TCP/IP. So that integrated platform is essentially what's allowed us to build a product that can be Dockerized and then provided to a client.
Right. Right. And how has been the OPC UA library helped in this application? Like, how has it helped you in building this application?
What we're doing would not be possible without OPC UA. I think one of the key things for us has been that the oil and gas industry has been very slow to migrate towards using OPC UA, but it is happening. And what we've realized by doing this project is that a number of companies out there are actually using OPC UA, but just not telling us. The real challenge that we've got is finding clients that will allow us to connect to their servers.
Right. And if I may ask, like, I know we have been working in improving OPC UA together. Can you list some strengths of OPC UA for people who are new to this? Like, what are the key features of OPC UA that you find is really helpful in the oil domain?
I think number one on the list is cybersecurity. You won't get anywhere trying to provide a product to a client if it's not something you can demonstrate can be authenticated, certified, and so on, so that it's cyber secure. That's the first question we get asked. After that, obviously, the next thing is OPC UA is built on the idea of an information model, and our clients understand the need to build hierarchies of information so that it's possible for us to access that information in a rational way using OPC UA. And then I guess the final point is our biggest concern, as you know, when we started talking with you, was whether or not we were going to get data communicated at the speed that we needed. And the answer to that has turned out to be yes.
We have another question here from Max, I think. From Gerard. I read it wrong here. In System Modeler running inside, is System Modeler running inside the Docker container or real-time data?
It's an executable from System Modeler that's being run inside the Docker.
Right, and this is a good point because you're saying you're using OPC UA to communicate, using TCP/IP protocol to communicate, but you also mentioned using the executable, which we haven't really mentioned today, that you have access to that too with an API, so you can, for instance, ping it with TCP/IP, and that's, I guess, is what you're using.
Yes.
Right. Then we have another question from Janos. What are the elements in Wolfram language to use as an OPC UA server or a client to connect to a physical OPC UA server? Right.
It's actually what you're using is a library to Wolfram System Modeler. So do you happen to have a model diagram with OPC UA used in it that you can actually share?
Unfortunately, what we've done is for a client, and they haven't given us permission
I was guessing that.
to share the details on it. So I can't.
Yeah, so let me click here and I can show, yes, and share my, that was a video. That's not what I'm finding a thing here before I, yeah, right. So let's take this and share my screen. Can I steal it for a bit, perhaps? I hope. No, okay, yeah. No, it doesn't seem like I steal it. But but for those interested, what you can do is you go into the System Modeler webpage, and then click Libraries, and you will find the OpenSUSE UA library. Then you can see screenshots of how it's connected, and it's basically the same drag and drop as you would do with any other Modelica library in a sense. It's just that it's that you configure communication with other systems with it.
Yes, and I've shared a link to the library store in the chat, so people can.
You're smarter than I.
For that. Okay. One thing I know, Robert, that you use the real-time simulate option in the Wolfram language to communicate with system modeler model. Is that true?
That's correct, yeah.
Has that been helpful, and do you use it? Like, how do you use it?
Well, what we've done, there's essentially two sides of what we have done. We have an in-house tool that we use as part of the design process for optimization, for fault injection, and so on. And that's built around Wolfram Language, WSM real-time simulate to bring the model in, and then running that model so that we can observe, what the impacts are of, for example, injecting faults and so on. So there's the in-house part of the tool, and then the client-facing part of it is where we export an executable and then put an environment around that allows us to display the hydraulic circuits using an HTML page. So for us, we wouldn't be able to deliver what we do without WSM real-time simulate. And I guess a question I was going to raise later was, can we get an understanding of where you're going with WSM real-time simulate, because it's currently kind of a little bit on the side of system model simulate.
Right. So it's a good question. I can't answer it today, but we'll have to get back to that. But we had with real time. Alexandra has a good question here too. Is whether you can run it faster than real time and use it to predict and do proper choices to get almost like a model predictive control, I guess. Would that be possible?
It depends on how complicated the hydraulic system is, and we are currently investigating that. So we would like to be able to do model predictive control. My gut feel is that for simple hydraulic systems that might be possible, but for the more complex ones, what we're observing with execution speeds is we may struggle to do that.
Yeah.
Right. Thank you, Robert and Konstantinos. It was a really nice presentation, and thank you for your insights.
Mm-hmm.
Next, we have Alexandre Lite from MWF Services, and his presentation will show how Wolfram System Modeler, combined with Austrian tools, forms a complete modeling and real-time simulation environment for rapid control prototyping and hardware-in-the-loop applications. So, over to you, Alexandre.
Thank you for the introduction. This title of this presentation could also be rewritten somehow as model-based mechatronics using Modelica, because in fact this is what we do. We just use a Modelica-based framework to run in real time some models of dynamic systems and use them to both design control systems and to verify what was already designed before. And the scope of this of this presentation starts with an overview about our activities here at MWF, our Modelica libraries, which were developed in-house and used in many different applications. And then I go through the specific applications in which we used all these Modelica libraries. After that, I provide a quick outlook about what is the current status of these libraries, what are we currently doing with them, and what are our plans as next steps for these libraries. So we started in 2012 working basically with product development, but very strongly with model-based product development. Not only electronic systems, but also mechanical, and currently we can say that we are specialized in mechatronic systems, both complex systems and other systems which are simpler and composed by many different devices and mechatronic subsystems. So our workflow is very simple. Once we have a specific Modelica development environment like Wolfram System Modeler, we generate a compiled version of the model called FMU under the FMI standard, and we run this model in real time under Linux with a preempt-RT package. After that, we are able to interact with the system in real time through real-world signals. I mean analog signals and digital signals. And we are able to do all this in real time with a rather complex dynamical system representation. This is one of our platforms. We call it Qfire Hill. As you can see, it has inputs and outputs for real-world signals, both analog, digital, and also digital buses like CAN bus, which is very common in agricultural machinery and commercial vehicles, for example, or even maritime applications and many others. The interesting thing here is that we are able to run we can run complex models with dynamics and event-driven behavior, even mixed with dynamics or just event-triggered behavior. We can run these models and see how the signals evolve in time and check how they interact with a real external controller by means of this platform. So throughout this presentation, you are going to see that we apply more or less the same workflows. We just change the specifics of the models and the applications, but everything is based on this very simple workflow. This could be done manually. I mean, we could generate the FMU and then adapt this FMU to run on Linux with real-time capabilities and communication with a data acquisition board, for example. But we have an automated workflow that allows one to generate an FMU and directly load it into this framework to run it in real time and interact with real world signals. So these are our main libraries. these names are the names that we use internally. We do not make them commercial, so we don't sell these libraries. We just use them in our own projects. We call them Aquanaut, Heavy Dynamics, and PMSMC. The Aquanaut library has models for vessels in the presence of waves, ocean currents, wind, and many other interactions with different actuators like thrusters, rudder, bow thrusters, and so on. The Heavy Dynamics library is mainly devoted to commercial vehicles, but especially commercial vehicles driving on hard soil. Another version of this library was developed also for soft soil and interaction with rocks and so on. I'm going to mention this very briefly, but this current version is dedicated to the simulation of heavy vehicles on hard soil. PMSMC means Permanent Magnet Synchronous Motors Control. This is a library that models accurately PMSM motors and generators and are able to help the designer to design specific control systems, design inverters, check the short period dynamics, and design other types of converters as well, like many different types of rectifiers, inverters, speed drivers, and so on. So they were all developed in-house completely, and they are used in our own projects. And now let me dive into our specific applications using each one of these libraries. First, a brief introduction about the Heavy Dynamics library. Currently, we use it to model and analyze and even design control systems for heavy vehicles. But originally, it was conceived to simulate planetary exploration rovers like this one that you see in the animation there. This is, in fact, an animation at that time. It was developed in, the first version was developed in Daimola, but it runs in System Modeler, Open Modelica, and many other Modelica-based packages. And as you can see, it is able to reproduce the trafficability of a planetary exploration rover with many wheels in contact with soft soil, in contact with stones, many stones at the same time, producing tracks on sand, different types of sand, etc., etc. Both sinkage, slippage, both lateral and longitudinal are able to be modeled and simulation in this library. This first version was very important to give us the basis for the development of the contact models, which are the most important features that we have in the current version of this library. Although it was originally conceived for both soft soil and hard soil, soft soil applications are not that frequent for us, and for this reason we further developed the library to work with hard soil only. And this is one of the most interesting applications that we have. This is an electric tractor, a four-wheeled vehicle. Although it in many situations it would be interesting to simulate it in soft soil, but it is entirely simulated in hard soil, and this is very useful for us to to help us to understand the dynamics of the vehicle, the power demand, how the power is demanded for every component and for every device in the power electronics uh, pipeline, and how the motors are going to be demanded during the specific use case. So this is one of the applications. Another one very interesting is this automated heavy vehicle. This is in fact this is an autonomous truck. Um, it was initially conceived to be used indoor, but currently we do not have access to the current developments of in the scope of this project. But at the time that we were involved, we used extensively our own library to design and assess robustness of the entire control system that provided autonomy for this vehicle. As you can see, it can be used to push heavy loads and maneuver them, and it is exactly as we expected. It is it is commonly used in contact with hard soil and not soft soil. So the heavy dynamics library is a very nice fit for this purpose. And this vehicle was able to travel many miles using the control systems that were developed using our heavy dynamics library. And currently it is still running based on these models, which were very accurate at that time. We did not have measurements in detail about the dynamics or even the geometry of the vehicle, and using the multi-body library, we could produce a very precise multi-body model. And um, while analyzing the uncertainties of the model, we could change some geometric details and verify if our control system would be able to achieve the the performance metrics that were meant at the beginning of the project. This is a current project. It's a smaller robot, and in fact, it's not just one product. Um, eh, it's two projects in one, because this basis is like an AGV, an autonomous ground vehicle, and this structural basis can be used to put a specific load on it, a specific payload, which is used to push feed to livestock. It is a very interesting application, and there are many robots used for this purpose currently. At least 5 or 6 different manufacturers are already doing their specific robots for this purpose. But the one interesting characteristic is that this is an AGV platform, which can be used to push any kind of load indoor, or even work as a feed pusher for livestock. During the design of this platform, we had to define accurately the amount of power which would be needed to drive the wheels, and to analyze the trafficability as well, by checking if the lateral slippage was too high or not, and if the control system would work even in the presence of many uncertainties, like the position of the center of mass, backlashes, and many other uncertainties that we know that we are going to have once the mechanical system is finally realized. So after materialization, we know that the final version of the robot is not look quite similar to the one that was initially predicted during the engineering design phase. We know that many uncertainties are going to take place, and even in face of these uncertainties, the control system must work and meet the requirements. And in this situation, the robustness assessment is a very important thing, because the mechanical design, electronics design, and even the control design of the inner loops for current control of the motors, torque control, speed control, and so on, they should run in parallel, and at the end they shall work seamlessly in perfect harmony. But they are always considering models during the whole process of engineering design. For this reason, robust assessment was very interesting, and in fact, this is one of the most important things that we do with these models. This is how a model with heavy dynamics library looks like. As you can see here, we have many components which are basically inherited from the multi-body systems library, like those rigid links, some joints which are inside the driveline model, for example, Ackermann steering model, and so on. But the most important detail here is this component. As you can see here, we have 4 wheels. Some of them are powered, some are not powered, and we have a precisely defined contact model for each of these wheels that produce simulations just like those you have seen in the previous slides. So this is how it looks like. This is a very simple multi-body model with contact with the ground. So the vehicle is completely free. There is no joint defining its relative movement to the inertial frame. This means that it stands basically on its wheels, and it solves the problem of static indeterminacy by considering a stiff contact between each wheel and the ground. Now let me talk about the PMSMC library. PMSM means Permanent Magnet Synchronous Motors, and C stands for control. This library, the main objective of this library is to serve as a toolkit to design and verify controls for motors and generators. We have many different models there, and they are modeled also considering multi-body library, because it would not be necessary to use the multi-body library, but as we want to integrate these models with those from, for example, heavy dynamics library or Aquanaut library, we are always trying to make them compatible with each other. As you can see in this picture, we have some motors which were designed based on this library, and some inverters and controllers that at some point have also details verified at this library in many different aspects, like for example the details about the gate drivers, about the SVPWM modulation, the magnetic and thermal characteristics of the motors, and so on. And this is basically conceived to be used as a tool for product design, and not like the previous ones, which were for were conceived for system design. So here the main results are products which were designed using the elements of this library. This helps us to check how the motors work in transient phases of the inner current loops, and check if uncertainties in the inductances or flux linkage or any other characteristic of the motors and generators would cause any type of difficulty in thermal with respect to the thermal management of the machine, or even any difficulties in controlling, for example, speed, position, and current of these motors. This is how one of these models look like. As we can see here, we have models for space vector, PWM modulation, three-phase inverters, current sensors, transformations from ABC frame to DQ frame, DQ to ABC, alpha, beta, and so on. And of course, the models of the motors themselves. The model of one motor is works like considering as the rotor being the plant to be controlled, a pure inertia with magnets in there, which interact with the electromagnetic fields generated by the stator. These items are modeled separately, and they only find they are only able to run in a complete simulation once you put all these pieces together. So looking into the details of one of these models here, like this motor, you are going to be able to see that the rotor, the stator, and any aspect of the windings, the thermal model, and so on, they are all designed in such a way that they only work if they are put together. And as in the real case, this motor is not gonna run if you don't have a closed loop for current, and subsequently closed loop for angular velocity as well. And our last set of applications comes from our newest library, the Aquanaut library. This one was designed to simulate vessels, most specifically for small tugboats. In this case, I'm not allowed to show too much details about this library because this is an ongoing project, and there are information from other companies that may somehow become available if I show some more detail. But as you can see, it's able to simulate the contact between a vessel, a pure hull with the water, and it computes buoyancy, radiation-induced forces, viscous-dependent forces, and so on. This is how it looks like. These components here at the right side are a hull, buoyancy forces, radiation-induced forces, ocean currents in this block here called stream. And just like in the previous libraries, it is 100% compatible with multi-body library. It allows one to run simulations and verify everything visually, just like those animations that I presented before. And it is very interesting to see. Also, we have the models of the waves that are also provided as inputs for this model. We can see if the boat is floating just like expected according to the motion of those waves. Just like in the other libraries, everything was based on a very concise and consistent basis of academic references. This one is mostly based on the works from Faltinsen and Torfossen, but there are other authors as well that were used here to help us to create the force models accordingly. So what are our next steps? First, I would like to remember that currently all these models, they are used in a very broad sense, because we use them in the phase of analysis. I mean, prior to having a materialized and implemented controller, we model everything and run many different analysis in virtual time, not in real time, and check how are the most probable experiments that we should realize. It helps us to plan real experiments with the vehicles. And additionally, we use these simulation models to design the controllers. After designing the controllers, we check if the controllers are sufficiently robust by means of robustness assessment. This means that after a controller is already designed with its topology defined, with the parameters synthesized, and so on, we keep the controller unchanged, and then we change the plant. By changing the plant, I mean we change the position of the center of mass, we change the friction coefficient of the surfaces, and many other parameters which are in fact uncertain, and we are only going to know them once we are able to run tests on the real system. But we want to know in advance how our vehicle is going to behave prior to the field tests. Mostly because these vehicles, they are heavy, they are almost always considering people around it and so on. And many in test conditions, it can be very dangerous to run these tests. So for this reason, the robustness assessment is almost mandatory during the control design. Um, Currently, what was not mentioned is that we take these very same models which were used to design and verify the, the controllers. We generate real-time FMUs with them, with the exact, the very same models, and export these FMUs to be used in our real-time hardware in the loop platform. Here you can see a worst case execution timing analysis. This is done automatically in our tool. Also, we have a specific model available. We run this worst case execution time analysis on our Linux preempt based tool, and it tells us in which rate it's able to run our models in such a way that we can tune our communication delays, our step size for the numerical integration, and so on. And the final controller, which is implemented in some off-the-shelf computer, can be tested against this very same model, but at this time considering real-time characteristics. It is not as before running on a desktop computer with no timing constraint. In this situation, timing constraints are already present there. And what we are seeking currently is deeper integration with Modelica tools, like for example, System Modeler. This entire framework, as you could see, was used and validated in many different projects. And what we think would be very interesting would be to have these two more seamlessly integrated into some specific tools in order to make it even more easy and straightforward to deal with. And that's it.
Right. Right. Thank you, Alexandre. That was really impressive, especially with the contact modeling, and those animations were fascinating. We have one question. Like, would you say that your library components can be used by non-Modelica specialist, mechanical and control engineers?
Perhaps he did not hear us.
Alexander, can you hear us, or are you muted?
Sorry, I was on mute. Would you say that your library component? Sorry,
So could a
I missed the
non-specialist use
question.
if a non-specialist gets
Is it
access to your library, would they be able to use it?
non-Modelica specialist? Yes, of course. Yes, they could. And in fact, this is what we do, because the team that develops the models is very small in comparison to the team that uses the libraries. And those that use the libraries, they are specialized in either mechanics, electronics, or even control systems, but they do not have a such a deep understanding on Modelica. They do have a basic understanding, but they would not be able to develop the library by themselves in a short period. So uh, yes, they are able to use it, and this is the main purpose. The purpose is to have access to the library, to use it in the level of the application.
Right. So I will ask you one question that I have been asking all the library developers. Like I see you do a lot of multi-domain models as well. So when you create your own libraries from scratch, what are the key principles that you follow during your library development?
This is very interesting. Um, so first, we are always trying to make it compatible with uh, the standard multi-body library. This is one a very important thing. And another one is that this um, power flow uh, and multi-port um, means of modeling that is usual in Modelica um, helps us to always keep track on the feasibility of the models that we are conceiving, building, and checking. Um, what we try to do is always stick to the first principles, to have every in every situation um, very simple situations that could be used as benchmarks for validation and plausibility checks. And only after that, we try to do more complex things. And the interesting is that when the simpler things work, and when they work well, and they are really well stressed and keep working, also go for more complex use cases, it works just as nice as the simpler ones.
Right. Thank you, Alexandre, for that awesome presentation. So now we have a few minutes left. So if there are any questions from the participants, please feel free to write in the Q&A panel, and we would be happy to answer.
There was one question more here from Sergio, and I think it was to you, Alexandre. If there are any specific tools you want to connect to from System Modeler?
Yes. What would be very interesting for us would be to have a more specialized connection between system modeler and um, control hardware, because this is most part of our models. They in subsequent phases of the project, they are going to be used to either um, model a plant that is or an actuator or a sensor that is going to run on a real-time platform, or even they are used to design controllers that are also going to run on real-time platforms. So it is somehow in the workflow that at some point you are going to deal with real-time platforms. So it would be very interesting to connect System Modeler with these kind of hardware platforms.
Right. We have one question from Robert Prince, right? Like, Robert is curious if you're using full RD fluid loading solution um, for your Equanet library.
If you're using the full RD fluid loading solution, the crawlers to run. Um, no, we have to to simplify many things to be able to run it in real time, because we shall not lose the feasibility of the models, but they shall be computed fast as well. And there are many implementation subtleties in which we have to take an approach which is more signal processing based than physics based. At the end of the day, they have the same effect. There are some simplifications, just like Cummings equations and so on. But we had to make some choices in order to make it simpler. It worked also like this in the past when we did another library for example, flexible bodies. It could take a while to make some computations according to the modes that were being considered, and we had to make some considerations to have a simpler version of the model. And what we try to do is to come up with models which are accurate enough and can take input data from open source softwares which are already in use by the specific community which is with, like, for example, I can give you an example. In this case of Aquanaut, there is a library called Captain that generates the added mass matrices and damping matrices and so on. This is a rather computationally demanding process. Everything which is related to potential flow theory takes a while to be computed, but most part of these things we do offline, and others we use a signal processing approach in such a way that we do not have at each integration step to look backwards to the entire history of the simulation. So this is a blend of many different techniques to run such complicated things in real time with plausibility and so on.
Right. Yeah.
Thank you very much. I think we're running out of questions. It's been a lot of information in 3 hours. I would like to thank Ankit for hosting us, and for those very attentive, might be wondering why we had a book stand here. It has books related to System Modeler and Wolfram Language. One of them is new, is this one. And I would like to conclude with just asking Ankit, do you know the author and what's the availability of the book?
Oh, it was authored by me, and it is available right now in Amazon. So for people who are new to System Modeler and Modelica, question like, okay, what is System Modeler? What is Modelica? How does it differ from other modeling tools? So I have been so much answering the same thing again and again. I thought it would be wise to write a book on it. So I've written this book, which is titled Thinking in Systems, Not Code. And it uses Modelica to model and understand complex systems. So people who are new to modeling or who wants to get hands-on to Modelica, you should read this book. And it is available on Amazon. Yeah.
So thank you, everyone that attended. Hope you enjoyed. And extra thanks to all the presenters. We really enjoyed it. And if you want to listen to this afterwards, it will be made available on several platforms. And most presentations, PDFs will also be made available. So thanks to everyone, and have a nice evening.
All right. Thank you very much, Ankit and Jan, for hosting this conference. to Sergio for helping with the Q&A, and of course to all the presenters. That's all we have for you today, but please stick around. We have a survey. In fact, let me share that with you right now. Remember that we have the recording of this event. It will be made available 2 hours after this session ends. And I think that's all. Thank you very much for being here, and thanks to all the presenters. Have a great day.